You know, when I hear an introduction like that, I just can't wait until I hear myself speak. I love the Peruvian people too much to try to give this talk in Spanish. So if you don't mind, I'll confine myself to English. You know, right now there are 300 million PowerPoint users in the world. As far as I know, 30 million presentations are done every day. Right now there's about 1.5 million presentations in PowerPoint being given. 90% of them are unbearable, according to a conservative estimate. 9.9994% induce deep sleep. Hopefully this isn't one of them. Although it is my occasion to have to give a talk like this in China, and I caught these two fellows sleeping. Unsafe pipelines. Well, you know, pipelines are a lifeline for us. We need them. We need them to transport hydrocarbons efficiently and safely, and by and large they do that. But pipelines in and of themselves are not dangerous or unsafe, but their design, their operation, and the product that they contain can certainly be unsafe. And so if we have small leaks or even major ruptures, they can lead to major consequences. Two pictures here showing the difference between a small leak and what happens when a gas pipeline actually explodes and leaves a great hole in the ground. Pipelines are relatively safe. When we compare the transportation modes in the United States, for example, for this particular year, it was about 2003, the people who were unfortunately killed as a result of direct involvement in a pipeline rupture or break in total amounted to 19. Most of them involved in distribution incidents where the line was struck going to their home or their place of business. If you compare that, though, with the number of people who were killed on the roads, 45,000, pipelines are by far a safe way of moving product around the country, no question about that. However, when they do fail, they cause fatalities, and we should be aware of that. These bar charts show progressively from 1988 through until 2009 the variations in the number of fatalities and the number of injuries that have been recorded in the United States. And you'll see that some years it's pretty low, and in others it's demonstrably high. If you look at the year 2000, for example, there was a major increase in the number of people who were killed. And as a direct result of that, Congress decided that they would take action, that they would force pipeline companies to address pipeline safety through the development of what are known as integrity management programs. And we're going to look at some of those, and in particular, the risk components of them. It's a huge challenge for a pipeline regulator or an energy regulator to develop appropriate performance standards for pipeline safety. And in particular, to develop a standard that's meaningful for situations that call for very low probability of occurrence, but huge consequence. It's a very tricky problem to solve. It's a problem that's not really amenable to regular statistical processing. These are infrequent events, but when they do occur, they can have catastrophic consequences, and we need to be aware of it, because what happens is the public just will not bear any pipeline explosions that involve fatalities involving children or old people, or indeed large numbers of people, and we'll look at that a little bit later. It puts tremendous pressure on a regulator to do something, to be seen to be doing something when pipelines rupture. So if we look at why do they fail, we'll find that for the most part, the major threats are due to about 8 sources. Corrosion. The word corrosion comes from the Latin corrodere, to chew away, and the metal is chewed away over time. External damage, where somebody has struck the pipe. Human error, which is common enough in terms of pipeline operations. The materials from which the pipelines are constructed fail, or sometimes it's just a natural phenomenon like heavy rain or earthquake or something like that, and they are sufficient to do real damage. And so the professional society that I belong to, ASME, have developed and issued a guidance document called the B31.8S document, which sets out an integrity management program and how to progress one. And in it, they identify 22 threats that could happen to a pipeline. There are actually 21, but just in case they forgot about one, they call 22 other. And other. We're not quite sure, so we better put it in there. But if you look at the 21 that are known, they break themselves down into three categories. Those that are time dependent, in other words, it takes time for the pipeline to deteriorate. That would be as a result of corrosion or cracking. There are others that are stable, and that sometimes comes about through manufacturing or construction. So pipelines that have been in the ground for 25 or 30 or even 50 years have benign defects, and then something happens and they awaken from their sleep and they cause major ruptures. And then there are time-independent events, and those are caused by people striking the pipeline. And if they hit a pipeline hard enough, the results are immediate and usually disastrous for the person who struck the line. And so we have to be aware of each of these. Weather, an outside force, sudden ground movement, for example, earthquakes, of course we get very little warning of those, and we'll look at those a little bit later. But the higher likelihoods are generally a result of internal or external corrosion, third-party damage, someone hitting a pipeline, or operators making a mistake or failing to follow procedures, equipment breaking down, material defects, or as they say, natural disasters. But the threats don't stay constant over the lifetime of the pipe. That's the thing that's difficult to track, because we'll find that over time, we'll see that corrosion and fatigue, of course, as a factor. As time progresses, the pipeline gets tired, just like a human gets tired. But if you look at the areas that I put the ring around here, it's increasingly obvious that some of these incidents are happening because of the competency, or rather the lack of competency, of the people who are involved. And it also speaks to the turnover of skilled staff. The number of people who are grey hair or who have no hair and are leaving this industry, and they're being followed into the industry by young people, which is great. But in between, there's a complete gap of people who never entered into the business. And so there's a huge problem of transfer of knowledge. And then we have a fundamental problem on the part of operating companies. Do they have the culture? Do they have the willingness to commit resources to do the right thing? So we'll find that historically people have been using incident rates as a way of tracking how safe things are, and that's fine, except they're regarded as a lagging indicator. They don't really give us too much proaction. They're all reactive, and instead we really should move toward trending and leading indicators, looking at what's happening or going to happen in the future as far as we can predict it. There are traditional approaches used to control threats. They come about through using standards. We've got lots and lots of standards throughout the world. Most of them originated with the ASME series of documents, the B31 series. And you use the B31 series 31.4, 31.8 for the design and construction of pipelines here in Peru. And that's the document that's shown on the bottom of this slide. In the United States, they don't follow the ASME standard, though the Code of Federal Regulation takes priority there, and it's a document that's issued by the Office of Pipeline Safety, the Department of Transport. But one thing that we should be aware of is that standards in and of themselves are not capable of covering off every eventuality that could happen to a pipeline. And even good practices are not sufficient to protect us. We've got to go beyond that and move away from the traditional approach and start thinking about risk. Now, one thing we will find that we have little or no control over as a pipeline operator is the consequence. Bad things happen, and we're limited in terms of our ability to control them. But one thing that is within our capability is the spacing of valves. If we put valves at the right positioning and they function properly, they will isolate the pipeline that has broken from its neighbour, and so fires that result, say, from a gas explosion will die out because they won't be continually fueled by the remaining product in the pipe. So valve spacing is a control measure that we have. But a modern approach to controlling threats is to use risk and risk management, and that's what I really wanted to complete the rest of this little talk about. And you will find that the United States Pipeline Materials and Hazardous Administration, the Office of Pipeline Safety, as it were, they said good engineering is only part of the solution. A strong risk-backed approach ensures the safety and reliability of pipeline infrastructure. So we need to think about risk and how we're going to approach it. In terms of how pipelines do fail, this is a list of the 21 culprits here. And some of them apply here in Peru. Some of them are extremely unlikely to apply. But you'll find that on the fourth column there at the bottom, vandalism, terrorism is an issue for you. The bottom of the third column, earthquake is an issue. And probably less so lightning and things like that. But nonetheless, we have to have a procedure for addressing each of these threats. In Canada, we've got some unusual threats where the pipe that was buried doesn't stay buried. In fact, these are two of my ex-colleagues sitting having their lunch on a pipeline that decided to come above ground. It had enough time below ground and it started to expand, and it took the easy way out, which was to come to the surface. And that's what often happens in our part of the world, where the ground can be soft, frozen, and then in the summer the ice melts and it pushes the pipe up. And so there's a fellow steps underneath that pipe in the second picture on the right. So it's a hazard that could happen very often in Canada, and could happen here as well, of course. But more likely what will happen here in Peru are geotechnical or weather-related events, where we've got a settlement where the ground can settle after a period of time, where landslides or slope movements would be a characteristic, where earthquakes might happen from time to time, or when we get very heavy rain, we'd have a washout of the pipeline and leave it just exposed to whatever debris comes into the river and strikes it. And so that's an issue. Or landslides, which is shown in the picture on the right. We're going to look at those. In a mountainous area, of which there are plenty here in Peru, we've got the problem of rock slides. We don't get much warning of those really, but when they do move, they move relatively slowly, so we try to keep an eye on them, especially after there's been very heavy rain, because that's usually the trigger for causing the rock to move. In Bolivia, or probably parts of the Peruvian jungle, you'll find that landslides are common enough, and when we get heavy rain, the ground will move. Fortunately, the tree cover provides some sort of stability for the ground, but not always. And so we see too that human activity can play a part. People living in neighborhoods that formerly didn't have a pipeline, and now they've built subdivisions, cities have expanded, and communities have grown around pipelines. And these people who are buying expensive homes, apparently they want hot water, they want toilets and things like that inside their home. It's unimaginable. But it means that they have to have pipes supplying them, and they have to go underneath the existing pipe, and that sometimes causes it to subside because there's no ground support or little ground support. And so we have geotechnical movements due to that. Geohazards such as seismic, where we will find that with very, very strong vibrations during an earthquake, the soil itself will not behave like a solid. It will start to flow like a liquid, and it will start to move the pipeline with it. So you sometimes find here, depending on how the pipeline's either going across the fault line or along the fault line, that will determine the nature of the response. But it certainly, the dotted lines there show that the pipeline undergoes a significant amount of distress when we have seismic happening. So those are all threats to the pipeline, and we need to look at them and perform risk assessments to to get a jump on them and take decisions. And so some quick definitions for us would be that risk is a combination of the likelihood of an event happening with its consequence. So likelihood speaks to how often it would be, consequence to how bad it would be. And so we would look at the combination of both of those. And when we think of risk, it falls into two categories as well, voluntary and involuntary. We need to look at how people react to those, because people judge a risk such as, say, smoking. That's a voluntary action, and they're willing to take a risk for that. But they're not willing to accept a pipeline blowing up near their home, nor should they. So you will find there's a big difference in how people respond to voluntary versus involuntary risks. I put some numbers on here to show you that the fatalities in the pipeline industry in North America accounted for 13 deaths. People being poisoned through drinking an unlabeled bottle of a liquid in their home, or even, I don't think it's eating a hamburger, but it's eating food that was had food poisoning, accounted for 4,100 deaths. In other words, you had a 300 to 1 chance, more chance of dying through being poisoned at home than you would of dying in a pipeline. How about that? You've actually got about a 60-1 chance of surviving being shot in the United States, which is heartening, I suppose, for some. The public don't volunteer to take risks around pipelines, that's for sure. So we have to think about how they perceive risk versus actual risk. And we need to manage, as far as actual risk is concerned, we need to think about all the things that could go wrong and attempt to reduce that risk to an acceptable level. For perceived risks, we have to communicate better to the public about what's really being addressed and what their hazards are actually amounting to. And part of that, when we come to manage actual risk, is look and place barriers between incidents that we know will happen and the consequence that could result. So we have to put layers of protection there between the incident and the event itself. And hopefully when you have enough of these barriers in place, we halt the progression here. And that's called the Swiss cheese model, after James Reason's work in the United Kingdom. And you'll find that when we have tragedies and you start investigating them, it's rarely one source or one particular causal factor, but many that have to fail for an accident to take place. And I've drawn on there a broken link, and that's exactly what it is. There's a weak link. When we come to perception, I draw your attention to the photographs at the bottom here, because, you know, a father tossing his child into the air, well, the father thinks it's a bit of fun, you know. The little fellow sees it as a little bit more risky, you know. But the mother, my goodness, how does she view the same event? So we have to be very careful about how people view risk, and we have to think about probabilities and consequences and the link between them, and making sure that when we're dealing with a toxic product or we're dealing with an explosive product, that we do put barriers in place to control them. So risk analysis will fall into two categories. One where we have not enough information to do a quantitative analysis, and so we're resorting to qualitative measures. And for that, we would make sort of a guess at what the level would be. We would use subject matter experts for that, and they'll categorize our risk as high, medium, or low. But the statisticians, they will convert that into a number, and that would be a quantitative approach. And so we're going to look at both of those quickly. But in terms of there are really three approaches. There's a qualitative, there's a quantitative approach, and in between we have semi-quantitative. Most of the risk models in the United States and Canada and Europe are of the second category. They're semi-quantitative. They take advantage of the knowledge of a subject matter expert, and they combine those with some hard data that's been collected for the system so that we can approximate the likelihood of failure. And so the analysis methods involve subject matter experts. We can have relative risk models where we're just simply interested in whether one piece of pipe is more risky than another. And the whole purpose of it is so that we can allocate resources properly, so that we can focus on the pieces of pipe that really are dangerous to us. And so we're going to come up with a model like high, medium, or low risk. And for the high risk areas, we're going to put some additional effort, as we'll see in a second or two. But quantitative risk, we would put a number to it. We'll take a probability of something happening at 2 by 2 in 1,000, 2 by 10 to the minus 3, and the consequence might be 3 by 10 to the minus 2. And when we multiply them together, we find that we've got a quantitative risk of 6 by 6 in 100,000, or 6 times out of 100,000. So that's how we go about doing something like that. For pipelines, we're going to look at the probability of failure, usually based on statistics. Consequence, we'll have to do some fairly elaborate modeling as to what might happen if a gas pipeline were to rupture and catch fire, how the radiated heat could affect people in buildings. But we do end up with a consequence number, and we can multiply both together to get a risk number. And then the issue is that acceptable, and acceptable to whom? So we're going to look quickly at that. So in terms of managing risk, we have to define it, we have to identify the hazards that contribute to it, we do our calculations, and then we find out, can we live with the result, or do we need to mitigate the risk? And that involves the expenditures of money, of course. So we're going to estimate, we're going to evaluate, and then finally we'll manage. So that's the process. No matter what type of approach we take, we'll find that overall we still have to find a strategy to reduce that risk to a tolerable level. We're going to have to do some form of cost-benefit analysis, and the regulator usually is not that interested in business risk. That's the company's issue. But for public risk, we have to think about what is a reasonable amount of effort that should go into protecting the public, and we'll see what that is and whether you agree with the approach. But risk reduction comes at a cost. It's not free. And so setting and communicating a risk criteria can be very challenging for people. We have this issue of tolerable versus intolerable, and whether in fact we should be taking all risks down to a tolerable level, and that would be an expensive business indeed. So we do have to find criteria that's based on human life. You may not like it, but your life is worth a certain amount. My life is not worth as much now as it was 30, 40 years ago, because I'm closer to 100 than I am to 0, right? My age, I'm 70 years old. So that means that my wife will probably only have to, from a statistical point of view, do my shirt washing probably about 150 more times, about another 3 years. That's my life expectancy, according to the Canadian Bureau of Standards. So we'd be thinking about criteria like human life, environmental damage, what's tolerable there. The regulator doesn't address business loss, but a business should be thinking about that. And we're going to think about the real challenge that comes about through trying to set an acceptance criteria. What does that look like? And what should we take, say, here in Peru relative to the rest of the world? Do we have the same standards? Should we hold the people here who are operating pipeline companies to the same standard as other parts of the world, or do you imply a higher standard? So let's have a look at that. Suppose you did have a pipeline break, and so the horizontal line there, which has got impact distance on it, it says there's a pipeline has broken, gas has escaped, and it's caught fire, and anything within that circle is going to be impacted. And we need to figure out what that looks like. We could find the gas release. Not every pipeline that's ruptured, gas pipeline that's ruptured, will catch fire, but about 1 in 3 do. And when they heat up, they release a tremendous amount of heat, and it's radiated out a distance, and so we have to calculate from that the exposure. And if you happen to be exposed to heat from a flame that could happen from a gas rupture, you can survive about 5 minutes if you're more than 300 meters or less than 300 meters away from the rupture. If you're more than 300 meters, you might be okay. You'd get badly burnt, but you'd survive. And so we have to do calculations like that. And engineers love this stuff, because it's quite dispassionate. We're just talking about someone. We don't know who it is. It's not my wife. It's not my relative. It's just some arbitrary person's exposed to this amount of heat, and what can they withstand? But what the regulator will do is to say, hey, you as an operator have got to go along the length of your pipeline, and depending on its pressure and depending on its diameter, if it were to blow up, anything within this calculated radius. And you can see here it diminishes for a pipeline that's 36 inches in diameter and operating at somewhere around about 120 atmospheres. The impact radius is 1,000 feet. So anybody living within 300 meters, if they came out of their house, they would be exposed to the heat and they'd die within 5 minutes. A smaller pipeline on the far right, 18 inches and 600 pounds per square inch, they only have to be greater than 100 meters away and they'd be relatively safe. So all of that we codify in Canada. We have in these graphs here for different sizes of pipe, for different operating pressures, how far the safe distances would be and how many homes should be within that area. Pipelines can't sterilize the land. You just can't build a pipeline and expect no one else to live nearby. That's outrageous. And so we have to come up with some sort of criteria for what's acceptable in terms of how close people can live and if they choose to live there, what is the level of risk that they're willing to take. And so we can build these plots of 1 in 10 to the minus 4, 1 in a million going out from a particular location. And we attempt to do that because we're of a mind that we have to, I jumped some slides here and I don't know why, but we are looking at what is in common parlance referred to as low as reasonably practicable. The test for us is going to be that we reduce risk to a level that we can live with and that we're willing to pay money to reduce. But there will be a level reached where no more additional amount of money will actually reduce the level of risk. And when we've reached that point, we've reached what's known as low as reasonably practicable. And that's a standard that's defined in law in the United Kingdom. It's a standard that's applied in Canada, and it's a standard that's used in Australia and beginning to come into use in the United States. And so we decide what is a reasonable acceptability for someone being caught up in a pipeline explosion. What's the reasonable expectation that they would survive such an event? And we come to the conclusion that it's about 1 in 10 to the minus 4. And 1 in 10,000, that we wouldn't go higher than that. Now, we get numbers, and you'll hear numbers like 1 in a million. To do that would be an outrageous amount of money required to go from 1 in 10 to the minus 4 to 1 in a million. And so we don't do it. Pipelines are a fairly safe form of transportation, but we do have to recognize they fail. They fail because people hit them or they corrode themselves over time, and we have to be careful about how that growth takes place, that we're monitoring it, that we use tools to find out how extensive the damage is, and we make timely interventions. Natural forces, when they happen, we have to protect the pipeline, we have to design the pipeline to withstand that movement. It means that for most of us, we're moving into an area, you will be moving into an area where instead of looking at the conventional way of designing pipe, when you're working in the high Andes or when you're working in a place where the ground is exceptionally unstable, you're going to have to move away from allowable stress design and move to what's regarded as strain-based design. And that's tolerable. It's used invariably in the offshore. It's the only way that you can actually design a pipe to be efficient and economic. And that's going to temper the whole of your design processes going forward when you go into these areas that are very, very hostile in terms of the land movement. Operator and equipment errors, we have to be careful that we have managed our failures there, that we have procedures in place to limit the damage that can occur as a result of, say, SCADA or supervisory control malfunctions. And theft and sabotage is obviously a challenge in many parts of the world, and that's why we bury pipe and try to bury it deep enough that people can't get access to the surface where they could do damage. At one part of my eclectic career, I looked after our pipeline in Colombia. And there are parts where the pipeline comes above ground. And so it was a constant battle trying to keep ahead of the FARC and trying to outsmart those guys. They blew up our pipeline. The refined product got into our river, and it killed 126 people because when the local people were scooping up the refined product from the surface of the water, there was a source of ignition, and the whole thing went sky high and took 126 souls to their death. Very, very unfortunate. So that's not what a terrorist organization wants to do. And so what they found out was they wanted to wreak economic havoc, and they found that the diameter of our pipe was exactly the same as the internal diameter of a truck tire. So they ended up taking truck tires and cutting them and then putting them around the pipe, but putting an explosive charge inside of the tire. And that had the same effect as blowing up the pipe without killing people, because it just choked off the supply. A major step forward. So my challenge there was to keep one jump ahead. And because I got that job because I come from Belfast in the north of Ireland, and my boss thought I should know something about bombs, so I don't know. You know, things with risk are not always as they seem. We have to be careful. When we see things, we can make judgments rashly, and we shouldn't do that when it comes to risk. It doesn't work that way. What we have to remember is that safety is our aim and object in all of this. So there were some slides I jumped over. I don't know where they went, but I'll be very happy to answer any questions that you have, and it's been my pleasure to have visited with you and to spend time with good friends at Oceaneric. Thanks very much.
Thank you, sir.
Well, the first thing that you're going to look at will be what are your real threats in that area. And in a built-up area, almost certainly it will be external interference. So you have to say to yourself, first of all, do people know that there's a pipeline there? So the first thing that you do to reduce risk, that it doesn't really tell you in the standards as such, will be to place warning signs. It says you should put warning signs. It doesn't tell you where they should put them or how far apart they should be. But that would be the first thing. And the second thing that you might well do is look at the access that people might have to the pipe, and you might determine that it's it's in your interest to put a plate or a concrete slab between the top of the pipe and the surface, so that if they do use heavy machinery for digging, that they're going to hit the concrete before they would strike the pipe. Now, you will not get any guidance like that in the standards.
Thank you. It's the only question. Es la única pregunta para el señor Murray. Muchísimas gracias a ambos, señor Galante, al señor Murray. Vamos a darles un gran aplauso a ambos.